Okay, well, welcome to the latest exam solutions run through for this Pearson Edexcel Physics AS, Core Physics 2 for the linear A level. So this is one that I gave as a practice exam to my Year 12 students this week. And Core Physics 2, for those of you who are not familiar with it, covers mainly waves and materials, but the last two questions can cover anything on the Year 12 content. So in this case, there's also electricity, a question about applications. So the last two questions can be on any part of the Year 12 curriculum. So it could be on forces. It's kind of like the practical skills for the Unit 3, but it's more, it's slightly different. So you'll have a look when you go through it, okay? So if you're doing International A level and you're revising for Units 1 or 2, then some of the questions here will help you as well, okay? So use it for IAL as well. The topics, the content for waves and materials is nearly identical. Okay. All right. So don't forget, if you watch my videos regularly, please like them and share them with any classmates who you think will benefit from having a look. Okay. And make sure you subscribe so you know when the next video is going to be uploaded. Okay. So the first question reads as follows: the wavelength of light emitted from a laser can be determined using a diffraction grating. Okay, so diffraction grating has the following formula. The equation used to calculate the wavelength is given, and you've got to decide which row of the table shows possible units for n and d. Well, n is like the order of the bright fringes, so it has no unit. So it's got to be A or B. And if you think about it, wavelength on the left-hand side of the equation is in meters. So if this is in meters on the left-hand side and n has no units, then sine theta is just a ratio. Yeah, remember, it's opposite over hypotenuse, isn't it? Yeah, so opposite of hypotenuse is just a ratio. So it has no units either. And d, therefore, must have the same units as the left-hand side. So d must also be in meters or a length unit. So the only one with a length unit is millimeters. So the answer is B. Okay? That's the first question. Question 2, it says a student carries out an investigation to determine the Young's modulus. They call it the Young modulus, but I keep wanting to say Young's modulus. Okay, which of the following gives two measuring instruments the students would normally use? Okay, so you need to use a micrometer, okay, because you need to measure the thickness of the wire, or the diameter of the wire, more correctly. So two of them have micrometers, so it's going to be B or D. You don't need to use calipers, but you do need to use a meter ruler to measure the original length of the wire that you're using. Okay, so the only one with the correct 2 is B. Okay, so the answer is B. Okay. Question 3 is about a dual beam oscilloscope. They call it a 2-beam oscilloscope. Yeah, it's used in a core practical to determine the speed of sound in air. Yeah, so this is another core practical. So you need to be familiar with how to use it. The oscilloscope's screen shown displays the signal used to produce the sound wave. So on the x-axis is time, and you can see here the period for a complete wave is half of the screen. So you can see 2 complete waves on the screen. Okay, and the time base, it says, is set to 50 microseconds per division. And the division is one of these small squares. Okay, so there are 10 squares or 10 divisions across. Yeah, so from here going left and right, we got 10 divisions. And if 5 of them are 1 period, then you know it's 5 times 50 microseconds. Remember, micro is 10 to the minus 6. So you need to know all your prefixes. Once you know the period is 5 times 50 times 10 to the minus 6, you can then calculate the frequency, which is what they want you to do. They want it in hertz, and frequency is 1 over the period. So this is no different from a GCSE question, and you'll see the answer is C. Okay? Hope that makes sense. Question 4. A ball bearing falling freely through a liquid reaches terminal velocity. So this is another core practical. So core practicals can come in the theory papers like they do in IAL, the International A level, and they can also in IAL come in the practical exam. In the linear, you don't have a third paper in year 12, but when you do it in year 13, you have what's called paper 3, which covers everything. So we'll have the practical skills, everything in there. It's the 2.5 hour exam. So you've got that to look forward to if you're continuing with the linear. I would say the linear actually is slightly easier than the modular, and the grade boundaries are lower than the modular. But the modular, because you're doing exams more regularly, they know you're only revising a smaller amount of content, so they make the exam more difficult. So it's kind of more depth in the modular because you can repeat it, and in the linear there's more breadth, so you have to remember a bigger amount of content for each exam. Okay, especially in year 13. Year 12 is pretty much similar. The terminal velocity in this experiment, when the ball's falling freely through the liquid, is determined, because it's reached terminal velocity, by measuring the time taken. So it's measuring the time taken for the ball bearing to fall a measured distance. So if you know the distance and you know the time, and then you can work out the terminal velocity. And then they're saying that the measured distance has a percentage uncertainty, and they're giving the value x, and the time has a percentage uncertainty. Okay? So whenever you do core practicals, you've got to consider how uncertain each reading you take is. And it depends on the resolution of your instruments and the difficulty in making those measurements. Now, they want you to find which of the following expression gives the percentage uncertainty in the value for terminal velocity itself. Because remember, terminal velocity is calculated by distance over time. So the distance brings its own percentage uncertainty, and the time brings its own percentage uncertainty. So to work out the percentage uncertainty of the velocity, you simply have to bring both percentages and add them together. Okay? Each value in the equation, each quantity brings its own percentage uncertainty. So the total percentage uncertainty would be x added to y, because they're both percentages, and therefore the answer is A. I'm using grey for yellow for reading through, and green for the answer or the solution. So really, I should have put this bit in green. That's how I've shown you how you get the answer. Question 5 is about polarization. A lamp is switched on and viewed through 2 polarizing filters, P and Q, and you're looking at it from the perspective of this eye. So the light is traveling through as shown. The lamp, it says, appears dark when viewed from P through P and Q. Yeah? Now then they say Q is rotated through 180 degrees. Whereas if it's dark and you rotate Q through 180 degrees, I've drawn like the grid. If Q's polarization grid is horizontal as I've drawn it, yeah, then rotating it 180 degrees, it will still be horizontal, so there'll be no change, it will still be dark, okay? So the fact that it's dark means that Q must be oriented perhaps in the horizontal, and P must therefore be in the vertical polarization. So if they're at 90 degrees to each other's crystals, which is what a Polaroid is, then light will not get through if they're at 90 degrees to each other. So you can see P and Q the way I've drawn it as a grid. You can see that's why light doesn't get through. It then says which row of the table gives the appearance of the lamp after Q again has rotated. First by 90 degrees, that's this one, from its original position, and then by 180 degrees from its original position. Okay, so if it is, let's look at 180 degrees. If it's rotated by 180 degrees, it won't change. 180 degrees won't change anything because it's going to go back to the same position. If it's horizontal, it will be horizontal. So if you change it 180 degrees, it will be the same as before, which was dark. Okay, so it's got to be A or C. But if you change it through 90 degrees, yeah, this is a change here. It by changing it through 90 degrees, they'll both be in the same direction. If you change the Q orientation, this one, by 90 degrees, the grid lines will then be this way, which is the same as P. Therefore, the light will get through and you'll get brightness. Okay? So the answer is 180 degrees will keep it dark, 190 degrees will keep it bright. So the only one with the correct 2 is C. And then the next one, question 6, it says a textbook describes waves as having oscillations of different wavelengths in multiple planes. Well, if they're in multiple planes, it's suggesting that they're unpolarized, whereas polarized will only be in one plane. And then it says the oscillations are perpendicular to the direction of energy transfer. So if they're perpendicular direction of energy transfer, they must be transverse. So the answer must have transverse and unpolarized. So here's transverse, transverse, unpolarized. Yeah? And all the bits which are not highlighted are not correct. Remember, only transverse waves can be polarized. Question 7 is about two thin converging lenses placed next to each other as shown. Yeah, each lens has a power of 4 diopters. I think that's how you pronounce diopters. Which of the following is the total power? Yeah, and that's just the addition of the two powers. So it's 4D plus 4D. So the answer is 8D, which is D. And that's question 7 done. In the international A level, there are 10 multiple choice questions. In the linear, each exam in year 12 starts with 8 multiple choice questions, so that's a slight difference. So a force extension graph for a spring is shown. Okay, they put force on the y-axis and they put extension on the x-axis, which is the way I like to do it, because then the steepness of the gradient is the stiffness constant. Okay, the steeper it is, the stiffer it is, and that's why we don't always put the independent variable on the x-axis. So it then says which of the following gives the work done, obviously in joules, in extending the spring by 0.15 meters. Okay, so 0.15 meters I've circled. So you then take the 0.15 up to the line, you can see it's 2.5, and the work done is the area in shaded underneath. It's really strange. The scanner I'm using, although I'm writing in blue, one page comes out colored and the second page comes out black and white. I need to talk to the technical team as to why that does that. Okay, that's fine because I'm highlighting it with color. All right, so work done is the area under the graph, which is area of triangle, so it's half the maximum force times the distance, the extension, yeah? And therefore the maximum force was 2.5, and the extension we were going up to was 0.15 on the graph, and the half because it's area of a triangle. So it's half times 2.5 times 1.5, so the answer is B. Okay? So that's the 8 multiple choice question. And here are the examiner's remarks. So you can stop the video if you wish to. There's questions 1 to 7 on one page and question 8 on the second page. Okay. Question 9. Bats use pulse echo technique to hunt for moths. Okay, I've recently done this with the S7. Echolocation, we also call it. The bat emits a series of ultrasound pulses which reflect off their prey or the walls of the cave, and the pulses are shown on the oscilloscope trace below. So you can see each of the pulses are emitted for a short amount of time. So obviously this is the amount of time, the width of these pulses. Okay, so the pulses have their own duration, and then you've got the time between the pulses, and that's the time t. So it says a stationary bat emits an ultrasound pulse that is reflected from a moth. The bat detects the reflected pulses 36 milliseconds later. So don't forget, milliseconds is 10 to the minus 3. So that means in that 36 milliseconds, the pulse goes there and back. Okay, that means it's 80 milliseconds to travel each way. Okay, so that would be 36 milliseconds converted to seconds divided by 2. Okay, that's the 18 milliseconds. All right, they want you to calculate the distance, and they've given you the speed of sound as 340 meters per second. Okay, so they want the distance between the bat and the moth. So the distance, I put it as D, should really use S in SUVAT equations, multiply the speed by the time to go there, not the time to go there and back, and you'll get 6.12 meters, 3 significant figures. And you can round it up to 2 significant figures because the data is only given to 2 significant figures. Okay? Okay. It then says the bat flies towards the moth. So it's getting closer. Explain why the bat must change the time between the emitted pulses as the distance decreases, the distance between them. So the way I've put it is as the distance decreases, yeah, as they get closer, time for the pulse to reflect and return, because remember it's got to detect it, is reduced. So the bat has less time to detect each of the pulses as it's getting closer. So what it needs to do, it needs to make sure the time between the pulses being reduced, that it needs to give out pulses more frequently. Yeah? So it needs to quicken its rate of sending out the pulses so that it knows the moth's position, yeah, as it's honing in on its prey. Yeah? By detecting smaller and smaller changes, it needs to send out more frequent bursts of whatever frequency sound they use, probably quite high pitched. So because the next pulse sent, yeah, the next pulse is sent once the reflected pulse is detected. Okay, and obviously the closer it is, it's going to detect it quicker, so the pulses need to be sent also quicker. Now, so I think this is quite a difficult question to put into words. So you just need to do your best, and this is where a lot of students will lose some of the marks. And there's another question done, so we do 6 marks, so it's 14 marks done. The total paper is out of 80, and here you can see the mark scheme that we just went through, 9A, 9B, and how many marks you get for each. 3 marks each, so you can just see them. Okay, they put the mark scheme landscape, and of course the exam is portrait, so it's difficult to squeeze them into the same PDF. Question 10. The speed of blood in a blood vessel, and change that back to yellow to keep to my standard. The speed of blood in a blood vessel can indicate a person's health. A high speed may indicate a high stress, and that would be on the walls of the blood vessel. Okay? So you can see the way I've underlined things when I'm reading it. I'm just making sure my reading is active rather than passive, and I don't miss any key words. Okay, so the words I'm underlining are thoughts that are going through my brain, and this is called active reading. I would recommend it. The speed V of the blood in the vessel with a diameter D, so the vessel is like cylindrical, we're assuming, is given by this equation. And then they told us that, for example, K is a constant, a numerical constant, because it has no units. Rho, Greek letter, is the density of the blood. And eta, this Greek letter, is the viscosity of the blood. So this comes from the materials topic. And then you can change the equation around because they want you to show mathematically that the unit for eta is PAS. Well, PAS, I start here. PA, pascals, is newtons per square meter. So I think you'll get 1 mark for doing this. And of course, then you multiply it by the second. So once you know that Pascal is Newton per meter, that's 1 mark. And then what I've done is I've changed the Newton into the Newton itself is a kilogram meters per second squared, because Newton is force, so that's mass times acceleration. So what I've done is I've changed the Newton to base units, and then you can then see I've put what was left from under the Newton, outside the Newton in there, and I've then added them in, and then I've simplified it. So when I look at Pascal seconds, it comes to the following base units when simplified: kilograms per meter per second. Now here we have the equation that they want us to analyze, and I've changed it to make eta, viscosity, the subject of the equation, and then I've put velocity v as meters per second, density rho as kilogram per meter cubed, and obviously diameter as d is a meter. So by knowing that these are the units of the top, I get another mark, okay? And then I simplify this, and I show that this also has the same units. Therefore, you could then show that you have proven that Pascal seconds is the equivalent to the units in the equation above, okay? So I think I started this at the beginning of the year with my students to show that any equation can be shown to, by units, to be equivalent. If the units on both sides aren't the same, there must be something wrong with the equation. Part B then says, as the speed of the blood changes, the wall of the blood vessels expand and contract. Okay? So we're talking about one blood vessel. I should have read it differently. The wall of a blood vessel contains collagen fibers. Collagen is a protein which basically keeps you healthy in terms of your skin, your joints, your hair, what else? Nails. So it's a protein. The graph shows the stress-strain relationship up to the breaking stress of the collagen fibers. So they're using Young's modulus for a natural material. So you've got stress times 10 to the 7 in newtons per square meter on the y-axis, and you've got the strain, which is no units because it's the ratio of extension to length on the x-axis. Okay? And the first question is asking you to work out Young's modulus. So I've done the gradient at this point, because that's where the straight line kind of doesn't go much beyond that, so the proportional part. So you need to use the straight line portion, and also it gives me nice figures of 0.05 strain and a readable, easily readable value on the y-axis. So I'm using those, and then I put my triangle that I'm measuring. I've put the delta y value and I've put the delta x value very clearly shown on my graph, and I like to do my calculations on the graph and then refer to it in the text. So there's the difference in the y. Obviously it goes to 0, so you can show that it's -0 if you wish. I think that's superfluous in this case, and then obviously gradient is delta y over delta x, and you can show the final answer to 3 significant figures, and of course it has the units of newtons per square meter, and this is what the next question is going to ask you to do. So I think you should show your communication on your graph. Okay, so that's just tip from the top. That's me. I've been doing this for over 35 years, so hopefully that will help you gain some more marks. So there you see, this question says calculate the Young modulus, which I've just done. Yeah, so that's the gradient of a stress-strain graph. Obviously it has to be the linear section. You've seen my graph already, and you can see the mark scheme in a minute. And then you could keep it in 3 significant figures, or you could change it to 2, depending on how accurately you think you know it. No data has been given, so it's all from the graph, and I think 2 or 3 significant figures, probably 2 is sufficient. The next bit says, describe the behavior, going back to my yellow color coding for reading the question, describe the behavior of collagen fibers when the stress is increased from the elastic limit. Yes? until the fibers break. Okay, so where is the elastic limit? Okay, this is what you've got to first know. So this is for Andreas really, because he seemed to get confused with this question, and it's not much beyond GCSE. Yeah, elastic limit is just beyond the proportionality limit. Okay, in GCSE I always give these notes, and so the proportionality limit on the graph would be roughly where we did the gradient. It will probably be slightly higher. So this would be the proportionality limit, P, and the elastic limit is actually the beginning of when it's starting to curve. So you could say the E, yeah. Let's just put this a bit more neatly. So the elastic limit could be the blue point there. So the green point is the proportionality limit, where the straight line stops. Slightly beyond the straight line part is the elastic limit, E. Okay? So they want to know what happens from the elastic limit to the breaking point. The question talks about that's the ultimate tensile stress. So the breaking stress is this point here. Okay? By the way, thank you for anyone who's been watching my videos over the last few months, whether you're new to the channel or not. And just, I would appreciate each video you watch to help with the algorithm on YouTube and to get more people to get to see these videos, because I think they are quite useful. You can revise at any time and you can switch them on and off when you want. Make sure you like each video, because that's how it works on the algorithm. And also share the videos with people you think will benefit from them, and make sure you're subscribed. Okay, so I know I also don't like many videos when I watch them, but in this case, as I'm making them, I've become more aware that content creators, they don't get their videos seen unless they get likes and shares and subscribers. So I now have 1,100 plus subscribers in just over a year, so it's about 100 each month. So thank you for subscribing, and I'm sure some people are no longer watching because they've already finished their A-level. It was nice last year when one student came back and told me that he got an A because he'd been watching my videos. So that was very nice of him to come back and show his gratitude. All right, so I think they will help you if you watch them. So please, just to show your appreciation, like each video and share it with anyone you think will benefit from it. Okay, so it says the elastic limit is just beyond the proportionality limit. So the stress strain, I'm doing it in the wrong system. The stress strain is no longer proportional. Yeah? Remember, once again, we want to describe the behavior of the collagen fibers when the stress in the fiber is increased from the elastic limit until the fibers break. So we're going beyond the elastic limit. So it's no longer proportional. That will get you a mark. And the fibers beyond the elastic limit are stretched beyond their ability to return to their original length. In other words, they have reached the plastic behavior phase. They behave plastically. And that means they will never return to their original length. Okay? As stress continues to increase even further above the elastic limit, a small change in stress can cause a sudden or large change in strain. And that's what we mean by plastic behavior. Okay? And the collagen fibers become less stiff. Yeah? Any fibers, whatever, we're talking about collagen in this case, they become less stiff when they go towards beyond the elastic limit. Eventually, the collagen fibers will tear or break. Yeah? And this happens at the stress value given on the graph of 8.0 times 10 to the 7 newtons per square meter, or a strain of around 8%. Okay? 0.08 was what it shows in the graph, which means 8%. So you see, I think there's at least 4 points that you can easily score from this way of explaining it. So I hope that makes sense to you, and then you can have a look at the mark scheme in your own time and see how you can improve the clarity and the level of depth and detail that you can communicate under exam conditions. Okay? Remember, I'm doing my answers, but I'm not doing them under exam conditions. I'm doing them for the sake of helping you understand the way you should write physics. Okay? And these are the most difficult questions, it's the qualitative ones. It's not like in maths where you can just put numbers in and keep getting the same solution each time because you keep practicing the same routine. In physics, you have to be able to do qualitative answers as well as numerical ones. In fact, the numerical ones are, I think, the easiest once you understand your maths. So here's the mark scheme. At the beginning, you had to show the SI units for velocity, rho, and diameter. So that will give you 1 mark. And you've got to show that pascals is newtons per square meter. And obviously, you've got to change newtons into kilograms meters per second squared. Okay? The gradient we've done. And then here are the 4 ways which should match my answers, which I'll let you stop the video and have a look at your own answers. Okay? And your practice should be to improve your answers after you finish each exam. Use these videos to use the purple pen method. In our school, we use purple pens for improvement. I want to see them. They need to be in your assessment folder. Okay? Each time you do a paper, you either self-assess it or I assess it, and then you do the improvements in the normal way. Okay? So the primary use of these videos for me is for my students, and it's just caught on YouTube and has allowed other students to also benefit from them. So sometimes people ask me for more up-to-date papers, and sometimes I put them in private mode because I need to use them as practice exams with my students. So please bear with me, they will be made available. For those of you doing International A-Level, I just released the January 24 Unit 5 exam. So for Year 13 students, which is equivalent to the linear paper 2. Okay, same Year 13 content. So go and have a look at that if you're doing either paper 2 in linear or you're doing the IAL Unit 5. It was from last year. I just had put it in private because I was using it as a practice run through with my students. And today they did that, those who turned up. In a demonstration, it says, of the photoelectric effect. Okay? So photoelectric effect is the photons releasing electrons. Electromagnetic radiation or photons of frequency F. Yes? So I would change this to photons. They probably didn't want to give away the answer. The electrons are released by photons hitting them, and each photon gives up its energy to an electron. Okay. So electromagnetic radiation of frequency F, or photons of frequency F, are incident on the surface of a metal, and if they have sufficient energy, then electrons are released. And the maximum kinetic energy, E max, of the emitted electrons, we call them photoelectrons because they've been released by photons, was determined for increasing values of F. So basically they increased the value of F, and they found what would happen to the kinetic energy of the released electrons, and that's been put in a graph starting from the minimum frequency, yeah, which produced 0 kinetic energy, to, as we went higher in the frequency, you can see the kinetic energy maximum is about 245 times 10 to the minus 19 joules. Okay? Remember the 1.6 times 10 to the minus 19 joules. Yeah? is 1 electron volt. 1.6. Is that 1? So 1.6 will be there. Remember that? You can change things from joules into electron volts, which you will do later. All right, so what's the question going to ask us? No photoelectrons, it says. No photoelectrons are emitted when the frequency of the radiation is below the threshold frequency, we call it. A certain value, they call it, because they didn't want to give you the term that you should know. Okay? Can you explain why? So another one, which is qualitative. You don't have to be able to do this in maths, but you do need to be able to get used to doing this in physics, and you've got to talk like this. The photon energy, E equals HF, where E is proportional to the frequency. In other words, the higher the frequency, the higher the energy. Now, I'm writing in bullet points. Now, how you choose to do it, you can take my answers and you can put them into bullet points yourself, or you can add a little bit. You've got to make sure you hammer the nail home for the examiner. You don't leave anything to his imagination. Treat the examiner as if he knows nothing, and that's when you're going to get more marks. Each photon gets absorbed by 1 electron. Yeah, so it's a 1-to-1 exchange. A photon can't share its energy with two electrons. So 1 photon gives all its energy to 1 electron. So that's what we call quantum physics. It comes in packets, discrete sizes. Okay, these are key words you need to know. There's a minimum energy required to get the electron somewhere from inside the metal to the surface of the metal. Yeah? So you know that. And this is called the work function of the metal. Phi is the symbol. Phi written like that, Greek letter. Okay, so we've done this in theory. Now you've got to be able to describe this. If the photon energy is less than this value, yeah, the work function, less than the photon function, it gains insufficient energy to get released or to escape from the metal. Okay? And there on the graph, there's where it crosses the x-axis. Okay, so if it's any frequency to the left of this value here, which is 5 point something on the frequency, 10 to the 14 hertz, anything to the below 5 point something will not release the electrons, okay? Because they end up with 0 kinetic energy. They might get to the surface, but they won't be able to escape it, okay? So I've then extrapolated this line back, so the line was only drawn up to here. I've extrapolated back to see that this would be the work function. So you're starting from this much below. If you reduce the energy further and further down, this is how much you need to get to the surface. Imagine you want to go from here to the 0 level. That's how much energy you need before you can even get kinetic energy. So this is the amount of energy required to get to the surface of the metal. Yeah, and anything above that then would be giving you some kinetic energy. Hope that makes sense. And this was a weakness amongst my students, many of them that I've marked already, in being able to describe this photoelectric effect. And it comes up every year in every exam. So you need to be really good at this. You need to practice every past exam paper you can get, including the IALs, which I've told you before. They have 3 sittings a year, and linear only has 1 sitting a year. So you can't just do the linear ones. You must do the international ones. It then says a photon with a frequency of 10 times 10 to the 14 hertz is instant on the metal surface, causing a photoelectron to be released. Yeah? So see the graph. Find the kinetic energy for 10.0 times 10 to the 14 hertz. That's the first thing. And you'll find that the kinetic energy at that value is about 2.9 times 10 to the minus 19 joules. Let's look at my graph. There it is. There's the 10. Draw the line up. Draw it across. It's just below the 3 value. So you could put it as 2.95 or 2.9. You can't put it 2.95 because they're going up 0.2s each of the lines, little squares. So that's 2.9. Yeah. Hope that you can see that. Let me just do that neatly. Okay, that's 2.9. Hopefully you can see that. Okay, back to the question. So we know the kinetic energy for the 10 times 10 to the 14 hertz photons gives this energy, and we also know that the equation for kinetic energy is half mv squared. So, and you can get the mass, here's the mass from your data sheet, yeah? So the mass is given to you on your data sheet. And so therefore the only unknown is v squared. Change the subject to the equation round, and if you make no mistakes, you can then square root it. So if I want to get v, I just square root from here. Yes. And once you square rooted it, you should get 7.98 times 10 to the 5 meters per second to 3 significant figures, which is 8.0 times 10 to the 5 to 2 significant figures, which is sufficient for the accuracy of this data. Okay. It then gives you, for the final part of this question, and I think I'm going to take a pause after that, the table shows the work functions, the work function for 3 metals, cesium, zinc, and beryllium. And this time they're given it not in joules, but in electron volts. Now, so I've shown you that on the intercept on the graph is the work function, okay, phi. And the work function from the graph, using my extrapolation, which means continue the line to the point that is the end of the graph, whichever direction you want to go in, allows you to determine just from the intercept the value. And there are other ways of calculating it. This is the simplest way. So once we know that the value is that, okay, you can then divide if you want to change it from, if you want to get it in electron volts, you divide the energy in joules by the charge of an electron, which is 1.6 times 10 to the minus 19, also from your data sheet. So you get 1 bit from the graph, 1 from your data sheet, and that changes the value from joules to electron volts for the work function. And you'll see that it's 2.3 electron volts, and therefore this is roughly the same as the value for cesium in the table. Okay, 2.2, 2.3. So you say that you have deduced that the metal used is cesium. Okay, another 8 marks. Okay, just have a look at the mark scheme. Thank you very much if you've managed to watch it all in one go. I doubt whether you have. Most students will stop, pause the video, do one question, and then go back and do some more in bite sizes, okay? And that's a good idea to do it that way. All right, so here's the mark scheme. I'll let you peruse as needed, okay? 11A, 11B1, and 11B2. Was there more to it than that? No, I think it's it. That's the end of question 8. And question 12 is about standing waves, which I'll come back to in part 2. I hope you found that useful. Once again, don't forget to like, share, and subscribe. I want to see the rate of likes increasing to as high as possible, and I need your support in doing so. Thanks for watching. Bye for now.